Good evening, everyone. Thank you for coming to tonight's Tech Talk. We're joined here today with Kevin Chow, who will be talking to us about database modeling. My name is Connie Johnson, and I'll be moderating our talk this evening. If you have a question for our speaker, please send a direct message to me, and I will present those at the end. We will answer as many questions as time allows. Before we get started, let's unmute ourselves and give our speaker a round of applause.
Let's go.
Let's go, Kevin.
All right, Kevin.
Woo!
All right.
All right, Kevin, take it away.
Hi, everyone. Good evening, and thank you to everyone for coming out tonight to my Tech Talk. My name is Kevin, and I'd like to start off by thanking CaseBlink for sponsoring tonight's Tech Talk. Tonight, the topic I'll be presenting is database modeling. So what is database modeling? Let's start off by answering this question. Database modeling is the process of designing the structure of a database system. This process usually involves diagrams to visually represent database schemas. We can essentially think of database modeling as laying down the blueprint for how your data will be stored and managed. Database modeling is a crucial step in the database development process, as it lays down the foundation for the efficient management of data within an application. It ensures that the database design meets the requirements of the system, while also adhering to best practices for data integrity, performance, and security. Database modeling in itself consists of several steps, all of which will be covered later in the presentation. So, what exactly makes database modeling so important? First of all, database modeling helps us organize our data effectively, aligning our database with the requirements of our software application. Second, by enforcing rules and constraints, we ensure that our data remains accurate and reliable over time. Sound database modeling can also optimize performance, making data retrieval and basic operations more efficient. Efficient data storage, streamlined querying, and reduced maintenance overheads result in lower operational costs and improved resource utilization over time. When done right, it also sets the stage for future scalability, as a well-thought-out database model allows our database to adapt and grow along with our application. Most importantly, by providing a structured approach to data organization and management, database modeling lays the foundation for the creation of a highly efficient and performant application. Now let's talk about some of the most common types of databases out there. On one hand, we have non-relational databases like MongoDB or Cassandra, which are designed to handle large volumes of unstructured or semi-structured data. Non-relational databases provides flexible schemas that scale horizontally to handle large volumes of data. On the other hand, we also have relational databases such as MySQL or Postgres, which organize data into tables with rows and columns, making them suitable for applications requiring complex queries. Relational databases typically scale vertically, meaning that you increase the capacity or performance of a single server by adding more resources to it in order to handle increased workload or data volume. There are other types of databases such as object-oriented databases, network databases, and cloud databases, but for the purposes of this presentation, we'll mostly be talking about relational databases and non-relational databases. Ultimately, the decision for a developer to go with a certain type of database is based on the different needs of their application. So, database modeling can be broken down into 3 steps, the first step being conceptual modeling. Conceptual modeling is the initial phase of the database design, where the focus is on understanding and representing the real-world entities, relationships, and attributes that would be part of the database. This is also known as the whiteboard data model, as we're not concerned about the implementation of the technical details such as database tables, columns, or data types. Rather, the purpose of this step in database modeling is to provide a high-level overview of the system structure and to help ensure alignment with the application's requirements. By focusing on abstraction, this makes it easier to communicate with stakeholders and adapt to the changing requirements of the application. This is most commonly done through ER diagrams. As we move through the different stages of database modeling, we'll see that the conceptual model is refined into a more detailed and technical representation that is then implemented through a database management system. Entity relationship diagrams, also known as ERDs, are graphical representations of the most essential components of our database. Entities represent the objects or concepts we want to store data about. Attributes describe the properties of these entities, and relationships define the associations between them. In summary, ERDs provide a clear and concise way to communicate the structure of a database to stakeholders, including developers, designers, and end users. Ultimately, they serve as a blueprint for the database design process, guiding the creation of relational schemas and ensuring that the database meets the requirements of the application. Logical modeling immediately follows conceptual modeling. This step involves translating the conceptual model into a more detailed and structured representation that can serve as a blueprint for the actual database implementation. Whereas conceptual modeling is primarily concerned with the what, logical modeling is more concerned with the how, through the filling in of the details of the ERD. At this stage, the database model has specified attributes, identifiable primary and foreign keys, and defined relationships between all of the entities. Overall, logical modeling transforms the conceptual design of a database into a detailed and structured schema that can be implemented into a specific database management system. It lays the foundation for physical database implementation and provides the framework for efficient data storage, retrieval, and manipulation. Normalization is also a crucial part of logical modeling, as this is where data is organized in a way to minimize data redundancy and increase data integrity. Let's break down the different normal forms from 1NF to BCNF. 1NF specifies that each column should contain indivisible values, and each table cell should contain a single value. 2NF specifies that there are no partial dependencies, meaning that every non-prime attribute must be fully functional, dependent on the primary key. 3NF says that there must be no transitive dependencies, meaning that no non-prime attribute should depend on another non-prime attribute. And finally, BCNF is essentially a stricter version of 3NF, in that all functional dependencies are based on candidate keys. It's important to note that normalization should be balanced with considerations of performance, as normalization can result in increased complexity and maintenance overhead. Physical modeling is the phase of database modeling where the logical model produced in the last step is translated into a specific database management system. From the slides earlier, this could be a NoSQL database like MongoDB or a SQL database like Postgres. Unlike logical modeling, which focuses on the structure and organization of data at a conceptual level, physical modeling deals with the technical aspects of the database, including storage structures, indexing strategies, and optimization techniques. This step plays a crucial role in the database modeling process, as it ensures the efficiency, reliability, and performance of the database system in production environments. To summarize, database modeling can be broken down into three main steps. One is conceptual modeling, where the model identifies the main entities, attributes, and relationships through the creation of an ER diagram. This is a high-level abstraction without any technical specifications. Two is logical modeling. This is where the conceptual model is translated into a more detailed and technical representation. The ER diagram is mapped to a relational model that has clearly defined tables, columns, primary and foreign keys, and other constraints. And three is physical modeling, which is the actual implementation of the database model into a chosen database management system. Here, factors like data distribution and partitioning should be considered. By following these steps, database modeling ensures that the database meets the functional and performance requirements of the application while maintaining data integrity and consistency. Here are my works cited, and feel free to connect with me on my socials. And thanks again to CaseBlink for sponsoring this Tech Talk.
All right, everyone, let's unmute and give Kevin another round of applause.
That was great.
Kevin.
Kevin.
All right, now let's address some questions from our audience. Our first question is from Zoran, and they ask, how does the process of normalization in logical modeling contribute to the overall efficiency and integrity of the database design?
Yeah, that's a great question, Zoran. I'd say that normalization probably eliminates data redundancy by organizing the database schema into smaller and more manageable tables. And because of this probably improves data integrity by reducing the risk of insertion, update, or deletion anomalies. Also, normalization can also improve query performance by reducing the number of joins required to retrieve data. And this, in effect, will lead to more efficient indexing and query optimization.
All right, excellent. Well, that seems like all the time we have, so we will conclude our talk here. Thank you all so much for joining us, and have a good rest of your night.